Okay, just now we stopped at continuity equation or conservation of mass equation. It is this one, these two. So what happens if you have a incompressible case? All right. Pitiba, what happened when you have an incompressible liquid? What happened to the density?
The density changes, sir.
If you have an incompressible fluid, the density will change. If you have a fluid that not able to compress or incompressible fluid, does the density will change?
Yes, sir. The density will change, sir.
Okay, so it's a little bit weird. So what happen? Let's say you have a cube, and this density, how you find your density? You take kilogram over meter cube, correct? Let's say you have a cube. So if you have an incompressible fluid, so this cube not able to compress, meaning even you apply an increase of pressure to the cube, incompressible means you're not able to compress it, meaning the outer diameter, outer dimension is same. So how, based on your argument or based on your statement just now, how your density increase? Can you explain?
Wait a second. So, as the shape changes, the density also changes, sir.
Yeah, but you are having an incompressible object here. You understand this English word or not?
Yes, yes, I understand, sir.
So the density is mass divided by volume.
Okay.
So you are saying you understand what is incompressible. So if you have an incompressible object, why you claim that the density will increase? What changes in this formula?
Actually, the mass will be when it's in compress, the mass will be the same also.
Mass
And
same,
also
volume the same or not?
the volume also should be same, sir.
Yeah. So how come just now you argue that the density will increase?
No, I didn't say the density increases, but I said the density will change.
How come the density will change?
Okay. I was because when the deeper we go, the shape. Yeah. No, sir, it doesn't change, sir. Actually.
Now you get it. For
Okay,
compressible,
sir.
density is constant. Be careful when you come to your FYP. There will be a question for me ask you about incompressible case. So when you become incompressible, density is constant. So in your formula, conservation of mass formula, the term that deal with density equals 0, because if you have a constant value and you differentiate it towards time, mean del over del t means a rate of change. So if you have something that doesn't change, So this term will become 0. So you can take out. Same with the right hand side, this one. Also you can take out. Then the conservation of mass equation will reduce. It will reduce only to the differential equation for x, y, and z direction. The rho you can take out. So when it's incompressible, the conservation of mass will reduce to this form. Will reduce to only x, y, and z changes in the velocity terms. So again, conservation of mass or continuity equation, you only talk about density component and velocity component. So if you are in the incompressible case, which means the density is constant, the rate of change of your density you can take out. You only left out velocity component. So you can write inverted triangular or vector component times the v equal 0. So this is what you simplify the equation when you have an incompressible flow. So when you do your simulation later on in ANSYS, when you take incompressible condition, inside the formula, it automatic, it will take out del over rho or del t equals 0. So the remaining calculation times will be very fast. You will take out the rho, changes of rho towards time, and you only compute the changes of velocity inside the control volume. Okay. The next question is, what happens if you choose a steady flow simulation in your case? When you talk about steady flow, right, all the terms that related to time will be, you can take out, right? So mean that all fluid properties will be independent of time. So in our continuity equation here, there's only one term that there's only one object or one component that related to time. Okay? Which means when it comes to steady flow, the first term here, this one you can take out. Okay, one you can take out. So when it's steady flow, your continuity equation will reduce to this form with a rho inside the second portion. Okay, you'll see that inside here, your differential or your partial differential equation, PDE equation, there's a rho inside x direction, y direction, and z direction. Only the density over t, this component you can take out. Okay, when it's incompressible, you only take out the rho term inside the equation. It means you take out this one, you take out the rho, take out the rho, take out the rho. You only have del u over del x, del v over del y, del w over del z. But when you have a steady flow, then you can only take out the density component in the continuity equation. You will left out del rho u in x direction, del rho v in y direction, del rho w in z direction. Or in short, inverted vector or vector component times the rho velocity vector. Okay. Look at one tutorial question, which is in your handouts. Question number 7. So let's say you have a simple case. You have a two-dimensional flow in a 3D in a 2D plane, in a XY plane. The x component, you're in the XY plane. X component of the velocity given by u. So let's say your u equal to ax. Determine a possible y component for incompressible flow. How many y components are possible? So we want to find, at the end, we want to find a complete velocity vector equal something I plus something j, because this is only xy plane. So xy, x represented by I, y represented by j. So we want to find what is the value in this equation. This is the message or the question want you to find. Okay, you are given this information. You have a velocity in u. So how do you convert this information into a global velocity component? Okay. So what is given? Given the information on the u component. I want to find is there any y component possible or not? And then, yeah, how many possible is it? So governing equation, because we are having incompressible, so rho component you can take out. All the rho component is constant. So continuity equation reduced to this form. So meaning continuity equation rho v vector equals 0. So you have this form. So we want to derive from here. Later we will have integration steps. So at this stage, before you start anything, you should able to call out the governing equation. So when you see incompressible flow, when it comes to test, you see incompressible flow, you call out the governing equation, you write this equation, you get 1 mark for this general equation. This is the evidence of your understanding what is incompressible flow in mathematical order. Okay, so this is how you score marks for this module. For incompressible flow, this is the governing equation. So for incompressible flow, all the rho component you can take out from the equation. This one reduced to this one. All right, on top, this one is continuity equation, reduced to this form. Then you look at two-dimensional flow in xy plane. Because you are having two-dimensional only. So the z components you can take out because this one is three-dimensional equation. You take out one of the component because we only look at xy plane. Okay. Of course, when it comes to your test, it will become a three-dimensional problems. So the governing equation reduced to the second form and further reduced to the third form. With this, you only have del u over del x plus del v over del y equals 0. Then, because you want to find the vector form, so we rearrange this equation. Del v over del y, because v is this one, del u over del x equal del v over del y. You put plus 0, you pull your del x to the right hand side, you get negative. So you know that your u equal to x, so you can differentiate this form. Du over dx, what do you get? Diba?
A,
A, yeah? Okay, good. So del u over del x is A. However, then you substitute inside this equation, you get negative A. However, although it's a negative sign, but it's still a constant. It's still a constant. So you integrate your y component because you want to see what happened in your y component. So you just expand, take this equation, integrate. All right. So v equal to integration of del v over del y and dy plus the remaining of the f function in x direction. Then you know that when you integrate this one, you'll get a y. Okay, because this one is constant. Del integrate dy, you'll get y. Y plus a constant value. Okay. So here, at the end, we get v equal to negative ay plus a constant value, or f function in x direction. Then you put in the vector form in x and y direction. Because this one you only have xy plane, so we don't have this component. This is in 3D complete vector form because we only look at xy plane, so we don't have z component. So you just put in the numbers that you calculate. So for this answer, the velocity equal u given by the question, u equal to ax, I, your v is negative ay, so you just substitute a constant value back into this general equation. So you have negative ay j. So this is the equation that we are looking at. Okay? And this one, this equation only apply in incompressible where your rho is constant, derived from continuity equation. Okay. So since incompressible already given in tutorial question, try to think about what if I change this question. Is it possible y component for steady flow? How many y component possible? So are you able to find for steady flow? Okay. Right, so this is some of the possible question that will come out. So what is given in the tutorial, it won't be repeated, but you will test it in your concept in another way. Okay. All right, we look at one more example, tutorial question number 8, then I think we call it a day. So this is another question, a long question that in a final exam standard or maybe in a test standard. So what we have here, so we have suspension system. This suspension system consists of piston and cylinder system. So at one instant, when the piston is L, so the L is given, L equal to 0.15 meter away from a closed end of cylinder. The gas density is given, rho equal to 18 kilogram over meter cube, and the piston begin to move away from the closed end at velocity 12 meters per second. Assume as a simple model that gas velocity is one-dimensional and proportional to the distance from the closed end. It varies linearly from 0 at the end to u equal to v at the piston. Find the rate of change of gas density, at that instant. So it asks you something about rho. Obtain an expression for the average density as a function of time. So it asks you what is the density in a function of time. Rho equal to something, equation, in the T format. Okay. So this is an application of the partial differential equation. And this one is under continuity equation, under unsteady condition. Okay. So we have covered incompressible flow. I give you one unsteady condition. So there's one more area that only we can ask you in exam. It is a steady condition, and of course some concept in incompressible and unsteady condition. Okay, we pull the diagram to one side. This is okay. Before we move forward, there's a velocity equation given in the diagram. U was denoted in the diagram. If you see, U means it's moved in the x direction. So the x-axis also given in the diagram. To the right is positive. Given by U, velocity equation, U equal to Vx divided by L. It means that the velocity is linearly proportional to the final velocity. Okay, there's a constant value there, x divided by L in the equation. So how do we start? Given a piston cylinder, we need to find rate of change of density and your rho in the t function. Okay, rho in the time function. So what are the governing equations? So again, this question is about continuity equation. So in exam, when you look at this kind of question, straight away, the first equation you write out, you'll get 1 mark. You write this rho over del t and the change of velocity equal to del rho or del t plus inverted triangular or vector dot rho v vector equals 0. From here, you will get 1 mark. Okay, here you get 1 mark. So because we know that from the equation here, your u equal to Vx divided by L, you know that partial derivative with respect to y and z is 0 because there's no velocity in the y and z direction. So if you go back to continuity equation, your y and z is 0. Huh? You just simplify based on the statement from the question, and you look at the diagram, there's no movement in y and z direction. So you go back to the continuity equation, you cancel out the y and z component. So your continuity equation only left out 2 terms inside there. Rho, the rho, del rho over del t plus del rho u over del x equals 0. Then you move your del rho over del t, because this is a term that we want to find for part B or part A also. Del rho over del t is the rate of change of density. So you pull the term, this one, to the right. So you have negative rho or del rho u over del x. And then if you break this term, del rho u over del x, you can write as rho du del x, del y del x plus u del rho over del x. This is partial differential equation or differential equation, right? So you have 2 unknown there. You can break into this form. This is fall under calculus. Del AB divided by del x. You can write A del B divided by del x plus B del A over del x. This is how you write when you have 2 parameter inside your partial differential. You can break into 2 terms. So that's why we can write del rho u over del x into the form that you see on the screen now. Then we continue with the calculation. Because we are having incompressible scenario, So our rho is assumed to be uniform in the volume. So partial differential of our density, del rho over del x, will be 0. So we can cancel out the second term on the right in the equation. Our equation left to be del rho over del t. We can we remove the limit. We remove the limit lim t to 0. You can change this del, the partial differential, to differential d rho over del t equal to the right hand side that you get on the screen here. You get negative rho del u over del x. Okay, so far we're still dealing with mathematics in the chapter of partial differential or differential equation. So far we get this one, and then since given u equal to v x over L, we want to find, because in this equation we want to find del u over del x, so we make full use of the equation given, u equal to v x divided by L, so we find del u over del x equal v divided by L. We put the x over here, put the x to the left hand side, then you have one partial differential equation. And then del rho over del t, just now the equation you have here, del rho over del t equal to negative rho del u over del x. Then you use the u equation to replace this one. Yeah. So at the end, you will have del rho over del t equal minus rho VL. However, your L equal L0 plus VT. L equal L0 plus Vt. How we know this equation come from? This is from this statement. If you read the question carefully, that equation is from this line. It varies linearly from 0 at the end to V equal to U at the piston. This statement gives you this equation. L equal to L0 plus Vt, yeah, from the statement. So you do the integration again. This one, you continue to use this equation. You integrate from reference density rho 0 to rho, and you integrate Vt over T dt. How we get that equation? We get from this equation. We rearrange del rho over del t equal negative rho V over L. We take the rho from right hand side to the left hand side, because the relationship between rho and V dl is a times. So when we move to the left, it becomes divide, right? Equal negative VL del t. Okay, so then we integrate both sides. Okay, integrate both sides. We will have this one, del integrate of your t, v dt, and the L you substitute from the linear equation just now, L equal to LO plus VT. So you know that if you integrate something over a dx, something 1 over in the integration, you'll get ln. So that's why from this integration products, you arrive at ln rho divided by rho 0 equal to ln L0 divided by L0 plus Vt. Okay. Now these steps to here is integration steps. So if you do not understand, go back to the calculus chapter under integration chapter. Right. Then you put back, remove all the ln. Then you'll get your rho in the time frame, in the time dimension, equal rho 0 times the L. If you after you take out the ln and then you do the simplification, you do rearrangement of the equation, you'll get 1 over this one. You put the LO down. You pull the LO down to the subdivision here. You'll get 1 plus Vt divided by LO. Okay. Then you back to the differentiation. So del rho over del t given by negative rho v over L by this equation. You just substitute the given parameter. Rho is 18, v is 12 meter per second, length is 0.15 meter. So the rate of change of density, if you times all the unit together, you will get negative 1440 kilogram over meter square dot second. So this is the rate of change of density. And on the left hand side, this one is the formula of the density change in the t function. Okay. All right. Next lecture, we're going to cover cylindrical coordinate system. We're going to stop here. Let me stop the recording.